beyond that, don't worry about it. I should maybe, let me qualify what I just said. Yeah, know that the 70S ribosome, but also know that ribosomes are made up of protein and ribosomal RNA. I mean, that would be legit. So protein plus ribosomal RNA, so the second type of RNA, and then again 70S. Okay, so that then brings us to that the messenger RNA, sorry, too fast. The messenger RNA is in the cytoplasm, found the ribosome, and now it's going to start making proteins. That's what ribosomes do, they make proteins. Well, I'm not going to insult you by asking you, what are proteins made of? It's obviously amino acids. So the ribosome, in fact, has to read the code of the messenger RNA and decipher that code, in other words, translate the code to choose which amino acids. The code or the sequence of the bases in the messenger RNA will tell the ribosome what amino acids to bring in. That's the translation. So that raises a real question, which is not something you would think of, but people work in this, they ran into it immediately. How many bases do you need to code for an amino acid? Now, for example, let's say we had a one-letter code. Now, one-letter code means this. We have 4 bases, so adenine, guanine, cytosine, uracil. If each base determines an amino acid, that means 4 amino acids. That's all we can do. This would be a one-letter code. Each one letter, each one base, gives us 1 amino acid. Now keep in mind, and you all know this, there are 20 amino acids in nature. We must have 20 codes. We have no choice. We have to have 20 codes for 20 amino acids. A one-letter code does not work. Again, one-letter code means each letter, each base, indicates 1 amino acid. 4 bases, that would be 4 amino acids. Can't do it. So then, we can try a 2-letter code. That's a 2-letter code. So we get 16 combinations. And each 2 letters, each code, would determine 1 amino acid. Better, but not good enough. The fact is, we must have 20. We have no choice in the matter. 20 amino acids, you have to have 20 codes. So 2, I'm sorry, no, they don't. The AU, I mean, the order is important. The order counts. So AU and UA are not the same thing. Otherwise, you'd really be in trouble. So 16 is better, but not good enough. So we have to go to a 3-letter code. Three-letter code would be like this. I'm not going to do the whole thing, but Now by doing this, we get 64. 64 combinations. Pardon me? Too many. I'm just saying we do have 64. I'm not saying we need them. I'm just saying they're there. Because a 2-letter code is not enough. So if 2 letters does not work, we have to go to a 3-letter code. By the way, in case you're kind of wondering how do I know this, well, besides the fact that I've done it before, there's actually a very simple formula. Y equals 4 to the x. Y is simply the number of combinations. Number of combinations. 4 reflects 4 bases. If we had 3 bases, then we'd have 3 here. So 4 just means 4 bases. X is the number of letters. So for a 1-letter code, we get 4 combinations. For a 2-letter code, we get 16 combinations. 3-letter code, that gives us a 64. So you could kind of theorize if you had a 4-letter code, if that were 4, we'd have 256 combinations. So it's quite easy to calculate. But at any rate, we don't need 4, we want 3. 2 is not enough, so we have to have 3. And that means 64 combinations.
Some of them must be inactive.
Pardon?
Some of them inactive.
Actually, no. The question is, are some of these inactive? No, they're all used. Hang on. They're all used. But before I get into that, because that's our next topic, let me give this a name. Codon. Codons are 3-base sequence that codes for an amino acid. A codon is a 3-base sequence that codes for an amino acid. So each of those would be a codon. So I was saying 64 combinations, I can now say 64 codons. Now, Solana was just asking, well, we clearly have more than we need, I mean, obviously. So are some inactive? My answer was no. The reason is this. And by the way, this next part I'm making up out of my head. I mean, everything I've said to you has been accurate so far. But now we're going to be talking about the genetic code. The genetic code is known. You can look it up if you want. I don't know it. I had other things to do with my life, like eat pizza, besides learning the genetic code. So here I'm just making up stuff. But let's say ACA, so I'm just giving you codons now. ACA, GGC, so 3 different codons. All 3 of these would be used to make the same amino acid. So all 3 of these, if they show up on the messenger RNA, they'll be used for glycine. Now again, I'm making this up. I have no idea what those stand for. Again, if you really care, go look it up. You know, it's in the book, it's on the internet, you can find it. But we really don't care. But the point is that for each of these amino acids, there will be 3 different amino acids that can code, 3 different codons that can code for the amino acid.
That must be true for a lot of codons then.
I'm sorry.
That must be true for a lot.
It would. So obviously there are 20 amino acids. So this would account for 60 codons. It's coming. I promise you, it's coming. So again, this was just an example I made up just out of my head. Glycine is a real amino acid, but the codons, I have no idea. But the point is that each one of the 20 will be coded for by 3 different codons. And if any one of those shows up on the messenger RNA, you're going to get glycine. So that is 60 out of the 64. We have 4 left over. But first off, any questions on this basic concept? And by the way, do you need to reproduce that? No. This, once again, is just simply information. The only thing you need to know is this, that the codon is 3 bases. To code for an amino acid, you need 3 bases. That's all you need. This is simply Y. So let me erase translation. So we have our messenger RNA. And something I'm sure you've never particularly thought about, but one messenger RNA molecule can code for more than one protein. It's not a one-to-one proportion, whatever. It's not one-to-one. You could have several proteins being formed off of the same messenger RNA molecule. And the way that works is here, here. So the X's are where you start the new protein. The Y is where you stop the new protein. So there's always going to be a starting point and a stopping point. You've got to have a starting point because you don't want to start halfway through. Now, for reasons I cannot tell you, the starting codon is the only one I actually know. It's AUG. I do not know why I know that.
You missed pizza that night.
I must have actually been in class that day. So the AUG is actually called the starter codon. The starter codon or the initiator. So starter codon or the initiator codon, either one is okay. But what that AUG does, that tells the ribosome where to attach to the messenger RNA. It tells the ribosome where to attach. See, the whole idea is you don't want the ribosome to attach halfway through. You know, there's an old joke I'm sure you've all heard. What's worse than biting into an apple and finding a worm in there? Well, the only thing worse is biting into the apple and finding half a worm. Well, you ate the other half. Well, that's kind of what this is. You don't want the protein to start halfway through. You want the whole thing there. Just like if you're biting into the apple, you want the whole worm. You don't want half of it there because the other half's inside of it. So the AUG is the only place where the ribosome can attach. So it's going to attach here, it's going to attach here, it's going to attach here. Different ribosomes. See, again, you can have more than one that's working away. And even inside the same place, you can have more than one ribosome. But let's just stick with one. So the ribosome attaches here. It's going to go all the way down until it gets to what I have here as Y. This would be the terminator codon. The terminator codon. For reasons I do not know, there's only one initiator, but there are 3 terminators. I mean, you kind of think it'd be 2 and 2, but it's not. So there's 1 initiator and 3 terminators. Now, in order to terminate the protein, you only need 1 of the terminators. You don't need all 3. You just need 1. So it's your stop sign, your stop codon. So, so essentially, the remaining 4 codons, 60 are used for making amino acids. The remaining 4 are basically punctuation codons. The punctuation codons means start and stop. Initiator and terminator. So again, 1 initiator, 3 terminators. And why, I don't know. But 1 and 3.
You don't know the differentiator.
Nah, I don't. I just know the one initiator. So what you have then, at any given moment, you can have numerous ribosomes that are working their way down the messenger RNA. You don't have to wait for one protein to finish before you start the next one, which is good, because remember, proteins are large molecules. We've spoken about that before. Proteins are large molecules. So if you had to wait for one protein to finish, that would really slow down the process. So you could have several ribosomes working away at the same time at different spots in the messenger RNA. So anyhow, those are the 64 codons. So what that really means is I need to qualify what I said here a little bit ago. Actually, I'm still going to use the definition. It's just easier. Codon is a 3-base sequence that indicates or whatever amino acids. But we've now seen there are 4 that don't do that. We'll just say, okay, we'll use the definition anyhow, but there are 4 that don't do it. Any questions? Yeah, Pierre.
You said you can have several ribosomes.
Protein is different than that protein. So kind of a yes and a no. But definitely on any given messenger RNA molecule, yeah, you can have numerous ribosomes.
How, I don't understand that,
What?
how different ribosomes could be working on the same messenger RNA but creating different proteins.
Well, remember, you have different sections. See, like here's your initiator. The
Right.
question is, how can you have different ribosomes on the same messenger RNA making different proteins? But you're kind of assuming in your mind that one messenger RNA is making one protein.
Right.
That's not the case.
Each
So-
section,
Each section makes a different protein.
so for each section that the ribosomes are working and they're making the
Right.
same protein,
Correct.
but
In a different section,
they're making a different.
correct.
I got it.
Yes. So all of these ribosomes here are making the same protein. All of these ribosomes are making the same protein, but different than the first one. And the same thing here. All of these are making the same protein. So in any one section, see with the limits of initiator and terminator, in any one section, all of these ribosomes will make the same protein. But going to a different section, different protein. So you can get numerous copies of the same protein coming at once, or you can get numerous copies of different proteins coming at once. Again, proteins are really large, as you know, hundreds, if not thousands, of amino acids long. It takes a long time to make protein. So this speeds up the process. Okay, I think that's really enough for tonight. Let's quit. Next Tuesday, there will be a quiz. And it'll be on everything up until right now. So, and by that I mean for the genetics, so genetics only. Any last questions? Okay, if you think of some over the weekend, go ahead and email me, I'll get back to you. Thank you all.